Hi there folks, welcome to this video which is titled C4.2 Standing Waves in Strings and Pipes. Now in this video we're going to be looking at standing wave patterns forming in different circumstances, and these are called boundary conditions. We're going to be looking at close, 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 open, and open, open. Don't worry if that doesn't make any sense to you, it will do by the end of this video. I've used the title C4.2 here because this follows the IB syllabus. If you have not watched C4.1, I suggest you go back and do that now, because we're going to be using some of the language and terminology from that video in this video. Equally, if you're not an IB student, I'm hopeful that this will give you a good account of just some of the patterns that you'll need in any standing wave syllabus. So feel free to keep watching. You'll obviously need some paper. You need a pen, hopefully a little bit of patience, because you're going to have to do a bit of sketching. Particularly if you're my students, you should have the worksheet in front of you, which has space in which you're going to do some sketches and be ready to write down some equations. So if you're ready to get to it, let's do it. We'll learn about standing waves in strings and pipes. Now, I mentioned in the introduction the idea of boundary conditions. Boundary conditions is a mathematical kind of tool. Sometimes we use it when we're doing integration. Don't worry, none of that here. However, for us, it's really going to decide what our standing waves are going to look like. So put simply, standing waves will form under certain boundary conditions, and those boundary conditions are going to tell us where our nodes and our antinodes go. So in this video, you're going to see three different types of standing wave. It's forming in three different conditions, and you're going to notice some similarities and differences between them. And really, those similarities and differences are going to be governed by the boundary conditions. You still may be unsure what I mean by this, so let's look at some examples. In the previous video, we looked at a standing wave forming in a guitar string. Now, a guitar string you might call an example of a closed system. We have two boundaries, both of them are closed. And what I mean by that is that both ends of the guitar string are fixed in position. Now you can see the profile of the standing wave on the screen here. You can see there that those extreme points on the left and the right, they do not move, and therefore that is where a node will form. In the case of this standing wave, the antinode, which is a position of maximum displacement, forms in the middle of the wave, and that's going to be something that we're going to be looking at. So this is an example of a set of boundary conditions that is, whatever wave is going to form on this string must have a node at the left and a node at the right. What happens in between really depends on the length and depends on what we do to the string in order to excite a particular mode. We'll come on to that later. There are obviously other boundary conditions. The opposite of closed would be open. So we might have an open system. And this, for an example, might be a flute. Now, if you think about this, when you're creating a standing wave in a flute, you are blowing at one end of it and producing a sound at the other end. Both of those ends are free to vibrate. You cause a vibration at your mouth, and there's a vibration at the end of the flute as well. The way that we depict this is using this kind of diagram. Notice the difference between the closed system. In this case, we have a free end at both sides, and therefore have to consider the consequence of that. Now, what you'll see here is actually we have a node in the middle of our standing wave. A standing wave which forms in our open system can have a node directly in the middle. What definitely forms at each end is an antinode and an antinode, because the antinodes, because those positions are free to oscillate with maximum amplitude. So hopefully you can see there's a big difference between the shape and the kind of profile of those standing waves depending on the boundary conditions that we're using. Closed has nodes at both ends. Open has antinodes at both ends. Now, obviously, if we can have closed, we can have open. We can also have closed, open, or open, closed. Now, it was tricky for me to think of some examples of this, but one example would be what I'm going to call a water cylinder. I think that's a terrible name for it. If you've ever taken, for example, a bottle of water, which is half filled, and you've blown into it and formed a musical note. That is the example of a standing wave forming in your water cylinder. Should have called it a water bottle, really. Now, what's happened there is the sound wave has traveled from your mouth, which is open, and through the top of the bottle, which is also open, and it's reflected off the water, which is closed. The water is fixed in position. And so therefore you have an open end and a closed end because the water is fixed in position, and it would look something like this. Just back to that water cylinder example, I might blow into this end, and then the sound wave would pass down, reflect, and form a node here, and then back up to the top again. So again, following those sort of patterns that we've seen in the first two, we have a node forming at the close end, an antinode forming at the open end. Let's remind us of those. Nodes form at the closed boundary, antinodes form at the open boundary, and these are always going to apply. Okay, so regardless of what system you're using, as long as you know you have a fixed point, there's going to be a node there, and if you know it's a free point, it's going to be an antinode. These are our boundary conditions, and there's only three that we will consider. Now, what we're going to do in the next slide is kind of look at the possible waves that can form in each of these boundary conditions. So I suggest you take a second just to digest this. You might want to pause the video, take some notes, whatever you want to do, before moving on to have a look at what the profiles are of each of the standing waves that can form in these systems. Okay, hopefully you've had a chance to kind of digest that. Let's look at this. Now, again, if you've got a piece of paper, you might want to do some sketching of this. I have stolen this image from goodness knows which website. It's been a very long time, so thank you to whoever created this. You've saved me a lot of bother. For you could at least have a try. We're going to look at the three different boundary conditions. Okay, we've got 1, 2, and 3. And we're going to look at the shape of the different modes that can be excited in each of these systems. I should say that we use the language harmonics and modes to refer to the different standing waves that can form under certain boundary conditions. So if we take the example of the picture that you've just seen here, we looked at some pictures like this one. This is what we would call the first or fundamental harmonic or mode. So first mode, first harmonic, fundamental harmonic. These terms get interchanged for our closed system. Notice here that there's some expressions here for speed and wavelength. Okay, we'll focus here on the wavelength. Notice here that if our string has length L, well, if we form half a wave here, then the wavelength of that first mode is going to be 2 times L. So for each picture that I show you here, it's going to show you the wavelength as expressed in multiples of L. So in this case, we've got first wavelength is 2L, and we would call that the n equal to 1 state. Okay, so there's lots of different sort of nomenclature and lots of different language that we might use to describe these. As I've said again, this could be called the first harmonic, could be the first mode, the fundamental harmonic, the fundamental mode, or the n equal to 1 mode. And expect sort of a mixture of those as you study through your course. This is the picture we saw before, and that is the fundamental mode for my string, which has fixed ends. Well, we've seen the other picture for a system which has open ends, and then also open closed. And you notice there we've got the position of our nodes and antinodes depending on the conditions. Now these, I'll repeat, are what we would call the fundamentals. These are the base frequencies or wavelengths that you would expect to see in this particular system. However, it is also possible, both theoretically and practically, to excite higher modes. And by higher modes, I mean higher frequencies. As long as we have our boundary conditions being met, then we're able to excite or produce other waves within our system. So let's have a look at the closed system for now. The n equal to 1 system has got half a wave and both points are fixed. There are 2 nodes and there is 1 antinode. Well, there's nothing to say that I can't create the n equal to 2 or second harmonic, which is this one. Now, as long as it satisfies my boundary conditions, this is a completely feasible state. You may not have seen a guitar string do this, however, it is possible under certain conditions to create this. Notice we've got now 1, 2, 3 nodes and 2 antinodes, and as long as we're fixed at both ends, that's absolutely fine. In this case, we notice we've got a full wave being produced here, and so therefore the wavelength of this wave is simply the length of the pipe, L. So this is the second mode. And notice in this case, all we've done is essentially add on half a wave each time. So if you're looking at that fixed or closed boundary condition, why not try and sketch the third and perhaps even the fourth harmonic and predict what's going to happen with their wavelengths. If you don't know what to do, simply watch the video and I'll show you how it goes. Hopefully you've had a try at that at least. No worries if you didn't really know what you were doing. As we said, when we went from the first to the second mode, all we did was add on half a wave. Well, we go from the second to the third. It's exactly the same again. Okay, we're just adding on another half wave. And we're noticing there that now we've got 1, 2, 3, 4 nodes, 3 antinodes. And actually our wavelength has decreased now. Okay, notice here we've got one wave here, and that is at 2/3 of the length. And therefore, lambda is 2/3L. And similarly for the fourth mode, it is adding on another. Notice we're going up higher frequencies and therefore shorter wavelengths. These are the first 4 modes of oscillation, or the first 4 harmonics for a closed system or a fixed end system. I really understand there's lots of language here, which is why I do encourage people to pause, have a little think, check that they understand what's going on here. Now, if we want to move on to the other systems, really the idea is the same. Let's have a look at the second harmonic of the open system. Well, as long as we've got an antinode and an antinode each side, it's fine. So what we're going to do is simply add on half a wave. However, that half wave is going to become in the middle here to satisfy that boundary condition of an antinode and an antinode. Notice now we've got an antinode at the left, an antinode at the right, and an antinode in the middle. No longer a node in this position here. The nodes occupy either side of the antinode. We're now going to look over our closed open and see if we can see what happens there. Well, again, we're going to add on half a wave and make sure that we still satisfy that condition of closed, therefore a node forming here and an antinode forming here. Notice again that we've changed the wavelength in both cases. In this case, we've got one full wave forming here, and therefore the wavelength is going to be equal to the length of the pipe. However, the interesting one comes in the closed open. Initially, we had a quarter of a wave being produced here, and now we've got 3/4 of a wave being produced, and therefore our wavelength has changed accordingly. We're going to do the same thing again. We're going to go through the third and fourth harmonics of our open and open closed systems. So I do suggest you take a shot just to pause the video, try and draw them yourselves, and then see if your drawings match what you're going to see on the screen. Let's look at those third harmonics. We're just going to add half a wave again, and again check, have I got an antinode at both ends? Yes, I do. I've simply added in half a wave. And again, have I got an antinode and a node at both ends? Yes, I do. Finally, these two images here. Now, this is probably very overwhelming, okay, and probably very sort of feels like a lot of information to take in at once. I completely agree with you. I think that the process here, really, when you're thinking about standing waves, is to first very simply identify what boundary conditions you're dealing with and remind yourselves of what they correspond to. So that idea that nodes only form at a closed end and antinodes only form at an open end is going to be really, really helpful for you. Now, in IB questions, they never tend to go much higher than the third or perhaps the fourth node. So reassure yourself that you're not going to have to memorize all of these. It's much more constructive to understand how they're drawn rather than to remember what each of them looks like in turn. Certainly those base level ones, I would hope that the first mode, the fundamental, is one that you would be able to reproduce because it's the simplest. However, and as we go from n equal to 1, n equal to 2, all we're doing is adding an extra half wave, and hopefully that helps you a little bit. One thing that you are going to have in your locker is an expression of the wavelengths. Now, we've said here, in every single case, we're getting a shorter wavelength as we go higher up. If you notice here, my fundamental wave is much longer than, say, my n equal to 4. Now, there are equations which you need to know for this. Okay, if we're looking at the nth mode, the nth wave, the nth harmonic, then for our closed, we have lambda n, so that's the wavelength of the nth mode, is equal to 2L divided by n. So if my n is equal to, I don't know, 3, we would have a wavelength 2L over 3, where again, L is the length of the pipe that we're considering, or the string that we're considering. Now, thankfully, that's exactly the same for our open. If we have a pipe of length L, we can take the length of it, double, and then divide it by the n of the mode. So if we're looking at the 8th harmonic, divide by 8, then you will get the wavelength out from that. Slightly harder is the closed open setup. That's a slightly different one, which is 4 over L. 4L over n, sorry. So if we have the length of the pipe, times it by 4 and divide it by n, you'll have the wavelength of the wave that you're dealing with. Okay? So, a lot to take in there. Okay, as I say, take some time to kind of process those, sketch them. You're never expected to sketch these perfectly. However, you are expected to be able to identify, for example, positions of nodes and antinodes. You should be able to count nodes and antinodes. You should be able to calculate wavelengths using these as well. Okay, and so I hope that that's kind of a little bit clearer now. I mentioned at the beginning these ideas of closed, open, closed being a very new thing for you guys. Hopefully this video has done something to clear that up. If you've got any questions, feel free to let me know and I'll be happy to clear those up for you. Thank you for watching.